That is an extraordinary display of seating organization, the likes of which have very rarely been seen outside of something or other. So anyway, I'm going to have to talk fast today. Thank God I'm in a place where people speak English. But anyway, I want to talk about machine learning, and in particular, I want to talk about techniques that really work and that you won't normally hear about. Techniques which are valuable, but which are not widely spoken of because they're not hard. Of course, in academia, they talk about the things that are difficult, not the things that work and are relatively easy to do. So my name's Ted Dunning. I work for MapR. Our booth is right over there. If I talk too fast and skip something, come on over and I'll talk to you whenever you come.
Ladies and gentlemen, the Keynote Theatre is now full. For all those still queuing, you're more than welcome to queue for the next session. The sessions will be uploaded onto the YouTube channel within the next couple of weeks. Thank you.
So, the situation right now is different from a mature landscape. A mature landscape, there's a large number of problems which are just impossible. There's a few that are easy, and you could be clever and find those. And then there's a border between easy and impossible, which is hard. But right now, the situation is very, very different. Because of technological changes, because of software custom changes, due to hardware changes even, we're in a greenfield opportunity where there's a vat of things that are highly valuable to do that are actually pretty easy. This situation won't last. A lot of people are going to be nibbling away at the easy, valuable things, and soon we'll be back to the mature landscape 5 to 10 years from now. In the meantime, there's a lot that we can do that's cool and still easy. Now, greenfield problems, these are the problems that are easy, that are going to be picked off, are easy, impossible, or hard, and the mature one, those easy ones are gone. So the reason that this is valuable is if you look at the value of big data. Imagine for once, I'm throwing money on the floor. I left my wallet over there, so I can't actually do that. When I start to pick it up, am I going to pick up the 20 first or the 1? I'm going to pick up the 20 first, short of being just stupidly insensate. And that's what happens when people analyze data. So if we graph scale on the horizontal axis, value goes up very, very quickly at small scale. That's because people are analyzing the most valuable bytes. The bytes that say, he owes me money, that sort of thing. Well, that's not valuable. Looking in his eyes, I can see that has no value whatsoever. But the idea stands that there are some value that are bytes that are totally obvious. But once you get beyond those first small percentage, you get into a region of diminishing returns. The value per byte becomes very, very small. And the cost of analyzing those bytes has to be correspondingly small. Historically, it has not. But now it is small. And so by increasing the scale, we can get a lot of value beyond that early phase of high-value bytes. But it is really, really big. We've got to have techniques that work to help us analyze that stuff. Changing the scale on the order that we're talking about, 1,000x or more, larger scale than we used to analyze, changes how we have to do things absolutely fundamentally. But there are green fields springing up. It's not like there's new low-hanging fruit. It's like we've lowered the entire tree. Most of these opportunities, even if they are dependent on machine learning, or AI, as some people trendily like to call it, are not that hard. The techniques are not that difficult. They come down to roughly counting. Here's an example. We had a customer who was looking at intrusion detection logs to try to find things. These log anomalies in access to a network. But they only log the things that you already understand are problematic, which means new attacks don't show. That means that defeating the attack that this particular customer was facing would have been impossible. But 2 years before, they had started capturing all of the headers on all of the touches from all of the universe. And it turns out the new attackers had their headers in an idiosyncratically inverted order. The order present in the attacking packets was never seen in the ordinary packets. And so in the full logs, looking at massive data, it was trivial to spot the attacker. In the small case, it was impossible because the data had already been scrubbed away. This is an example, the simplest kind of example, as to why scale matters. Fraud detection. In small case, you have a very narrow profile per user, and you can detect some kinds of things. In the big data, you can look at the exact pattern of transactions. I buy petrol at a particular station. I buy food at 2 different stores. If I suddenly change that, I've had an aneurysm or it isn't me. But unless you look at the details of my habits, you can't see the change. So finding fraud with big data is easier than small. Now, just a cautionary note, easy and stupid are not the same thing. It's easy to be stupid, but easy techniques that work well take a little bit of study, and you need to figure out, talk to people about what's really working. It isn't that you can just do anything you want. That doesn't work. So let's talk about some of those today. Scale does not cure wrong. It just makes easy problems more common. So one of the simplest things we can do is look at whether things co-occur. Do they occur together? These 2 guys are sitting next to each other. This is the first time, as far as I know, I've ever seen them. So once in my life, out of many thousands of people here, I see them together. Is that interesting? Nah. But if I saw them together now, and I saw them together at the booth later, I would appreciate it that they came to visit, and I see them at another presentation together, at some point I begin to say, something's going on. Maybe they work together. Maybe something else. But suddenly I begin to say, this is not just a chance co-occurrence, but there's lots of people here sitting next to somebody else. So there's a lot of co-occurrences happening here that don't matter. So what we need to do is count the number of times I've seen anybody, those 2, together, seen one without the other, seen the other without the one, and how many times have I seen other people standing next to each other? That's all it really takes. That and the ability to decide which of those tables are interesting. There's a slide here with a reference in it. We don't have time to get into it, but the fact is, if we look at tables where A and B co-occur at the rate you would expect anyway, those are boring. We'd look at tables where there's no data. That's the upper right. It's boring. As we go to the lower left, we have 2 people that I've seen out of 10,000 today sitting next to each other. Well, that might be interesting. But there's a lot of those. But if I were to see 10 times the same people together, never see them apart, and have seen 100,000 people, then I go, there's a pattern. There's a very simple way to put those numbers on that, and being able to find things that co-occur lets us build some very interesting systems. It's that simple, literally. Count and find co-occurrence. Count and find behaviors that lead to other behaviors, other susceptibilities, other interests that you may like. The leading behaviors that co-occur with the target behaviors we call indicators. And we can put those indicators into a textual search database, and we can now search with behavior. As easy as that. Let me show you an example of what that gets us. Looking at the histories of people here, here we've got Alice, Bob, and Charles, and they've done apples, puppies, ponies, and bicycles, and so on. And apples and puppies co-occur in Alice and Bob's history. We can count those co-occurrences, and we can then make check marks where we find indicators. Apple happens to be an indicator for puppy here. We don't find any indicators. Ponies are not an indicator for anything because everybody wants a pony. So we find the interesting cases. Those are indicators. And here's what we could do. I took 1 million videos. I took about 10 million people's viewing habits. This was years ago. And we looked at the words that people said when they were searching for things. And we used those as indicators for videos that people searched for. And then we went and we gave it the query Paco de Lucia. Paco de Lucia was a guitarist, started with Spanish classical music, especially flamenco, and then moved on to what he called new flamenco, a jazzified form of that type of music, inspired by that. Conventional search finds nothing. I guess that's a nice way to say that. But recommendation-based search with indicator behaviors finds some very interesting stuff. Here is the conventional search, and what we find is a whole lot of Spanish daytime television, hombres de Paco. 2 words in common with the query, and it means nothing. Here are the recommendation searches. The top hit, Ciudad de las Ideas, is a Spanish classical piece of music, but look at the guitar that he's playing it on. It's a semi-acoustic jazz guitar. So remember, there are no actual Paco de Lucia videos in this test set. But remember I said that Paco de Lucia's guitar playing was a blend of classical and jazz influences, which is precisely what the top hit is. The second one, a bunch of women dressed in black, happens to be CUD, a flamenco dance group. The system appears to know that flamenco music, flamenco dance are connected. Flamenco, out of the Jewish tradition in Spain, is connected to Spanish classical music, which then is connected to Paco de Lucia. No, all it's discovered is that the users know that, and so the behaviors they exhibit take us to interesting content. The third one is a classical piece. The fourth one is Van Halen doing a classical riff during a concert. The last one is a kid in a dorm room imitating Paco de Lucia directly. So we can do that very cool thing with co-occurrence and conventional search. Now, it may require big data in order to count enough things, but this isn't hard. This really isn't hard. We could do document classification better than almost any other system. We can identify language. If you give a system like this a page of text, it can learn to recognize that kind of text. We can do species identification. We can identify the species of a short snippet of DNA, having seen only a tiny, tiny smattering of it before. We can do things that actually make you money too, not just make you virtuous. For instance, if my credit card is scanned somewhere, you know, it's got a chip on it, but it's still got a mag stripe on the back, and it still has the number on the front. So somebody could steal the key information off of my card if I ever let it out of my sight, and then they can use it to commit fraud somewhere else. But finding the place that they stole the data is difficult because they don't commit fraud there. They commit fraud everywhere else. So you have to look at the entirety of everybody's experience, the entirety of all of the transaction they've done, and find what co-occurs with fraud. What are the indicator behaviors that ultimately lead to somebody being a victim? So let's find merchant zero. Merchant zero is where people go. That's where their data's been stolen, and then fraud occurs somewhere else. And we're going to look at all these somewhere else's and find merchant zero. By doing that same sort of co-occurrence thing with simulated data, you can see the compromised merchant comes up out of the noise away from all of the other merchants, just by counting and finding co-occurrence. In real life, on real data, it worked even better. Let me repeat that. That was really, truly bad guys. It was really cool because it was also where the head of the bank's security system had lunch very commonly. It was right next to his house. He had no idea they were stealing his data under his nose. The fraud rate in that place was lower than average because the guys were protecting it. They didn't want any attention coming to that. We checked with the Secret Service, and it was a den of skimming. So simple stuff can do amazing results. I'm going to show another example. This is a bit more like advanced machine learning, in spite of the fact that it has chicken in the name. But it has tensor, which is a very fashionable tech keyword right now. So the problem here is that a friend of mine has a chicken coop. He has chickens in it. They lay eggs. He thinks that's cool. But so does a certain blue jay who comes in and pecks the eggs. My friend, who's normally a friendly, pacific sort of guy, would like to do dire things to the blue jay. So he would like an automated system to do that. And so he would like a system that looks at the hen house and figures out when there's a blue jay there. This used to be hard. There's a thing called the inception model. Google built it. They did amazing stuff with image recognition. It's really complicated. But they open sourced it. And you can take the inception model and you can retrain it. So traditionally, machine learning goes by taking vats of data, you do learning, you produce a model. A model is a thing that makes decisions for you. You give it more data, and you make decisions and actions, and world domination sort of follows. This is the Silicon Valley business plan for machine learning. But we can do it differently, because that requires vats O data, which could be hard to come by, because this has to be vats of labeled data. Somebody has to go and mark millions of images to make that work. Here's a simpler idea. Let's train in one domain. In fact, Google has already done that for us. And let's retrain on the domain we want, the chicken coop. So we train, get a model. They did that. We take that model and we do retraining just to adjust it slightly. Because there are regularities in the universe, that can work. And that gives us a new model that we can make decisions just in an afternoon and profit world domination. So Ian added a few thousand pictures of chickens, empty nests, and blue jays, and he had something that recognizes it. So in the upper left, that's a Plymouth Rock type chicken. In the upper right, that's Ian's arm. You can now recognize him. He's an international hand model as the result of this work. In the lower left, there's more chickens. The middle bottom is a Rhode Island red. And in the bottom right, there's a blue jay about to peck an egg. Now, he hasn't quite figured out what countermeasures. Being an engineer, this was the fun part, but he would kind of like to make this into the hall of horrors for any blue jay who comes in, but he doesn't want to traumatize the chickens. If you have ideas, send them to me. But the system can recognize exactly what these are. It's a webcam and a Raspberry Pi, and it can spot the blue jay. This was cool. This wasn't hard. That cross-learning, that transfer learning made it possible. So the summary, 30-minute talk, not a whole lot of details. Catch me more for more. There are easy techniques that are facilitated by having access to enormous data, that are facilitated by having easy access to computational power. Co-occurrence and transfer learning are the two I've talked about today. If it's not just blue jays you want, you can figure out how to make this happen. Public service announcements. This is me. I'm Ted Dunning. You can talk to me anytime. Hit me by email, by Twitter, or in person. You can get books that we've written on these topics. We're going to be signing some of the latest books about machine learning model management. That's going to be Ellen and I. She's a habitual co-author of mine. The book that we're going to be signing, there we go, the Pony book is the one that talks about co-occurrence. The book today is talking about the logistics of how do you deploy these things practically. You can download these books for free, all of them, or you can buy them from O'Reilly. And I'd like to put a last-minute plug in. Traditionally, for mysterious reasons, women haven't been going into big data. There's a huge lack. I can't necessarily figure out why, because the women who aren't there, I can't ask. But I'd like to just put a plug in and a reminder that everybody can do this. It isn't just guys who look like me with PhDs from wherever. A lot of different kinds of people can do this, and a lot of different kinds of people should be doing this, because the key to success with these techniques isn't the techniques. It's not the wand, it's the magician. It's the goals that you have, the decisions you can make. And so, yeah, our neighbor's kid who wore those beautiful slippers should grow up thinking she can do this, but so should you, anybody, anytime. So come, let's have some questions. I think we've got 2 microphones that are about to wander around. Anybody got some questions, comments, or was that too fast? You know, I'll assign questions if you don't have any. Well, then we could be back on time then. We really would love to engage with anybody who'd like to come talk to us, talk to me, right over there in the red booth. Thank you.